All right, so we stated this theorem. If we have an integrable sequence of functions, and if they converge uniformly to some function, then that function is integrable, and moreover, its integral is equal to the limit of the integral of these integrable functions. Okay, that's the statement. Okay, so let's prove this. All right, we use just, of course, definitions. So let epsilon be given. Okay, choose and 0 so that uh, n greater than n0 implies this distance, the submetric between f and fn, is less than epsilon over 3b minus a. So my interval is ab. B minus a is a positive number. 3 times that is again positive, and I divide my epsilon with that positive number, whatever that is. That's my epsilon for this definition of uniform limit. I use that epsilon. Now, since each fn is Riemann integrable, fn0 is Riemann integrable. Fn0 is Riemann integrable. And thus there is some delta positive, so that if you choose any partition, so that for any partition P of AB with norm of P, so the length of subintervals is less than delta, then the distance between upper and lower Riemann sums the difference between these two is less than, let me choose epsilon over 3. Okay. Yes. This is always something positive, of course, because this is larger than this one. All right. Now, since the distance between f and fn0 is less than epsilon over, right? So distance between f and fn0 in particular is always less than this, and this implies, so since fn0 x minus f of x is less than epsilon over 3b minus a for all x in 0, no, ab, the okay, distance difference between the upper and lower Riemann sums. Okay. This is less than epsilon over 3, and this is less than epsilon over 3. I will explain this on a picture now, why this is the case. This is because of the following. You see, I have this interval AB, and this is my, let's say, function f and 0, and I have this ball around this of radius how much? So this distance is less than, okay, let me choose different color. So this distance is less than epsilon over 3 times b minus a. Okay, right? Fn and my function f is inside this. So this is my f. So if you have any rectangle, partition here, let's say ti and ti plus 1, you look at what? You look at lower or upper Riemann sums, for this partition. The height, the upper or the supremum and infimum of f and fn 0 will be at most this much, because the distance between these two graphs is at most this much. So the supremum over this interval and infimum over this interval is less than epsilon over right. So supremum of f and 0 okay, f and 0 x or t, maybe t is in ti and ti plus 1, this supremum, and the supremum of ft as t is in this interval, this supremum is always less than epsilon over 3 b minus a. So the height of the rectangles is at most this much differs. The total base of the rectangles is b minus a. So if you compute the areas, the difference will be less than epsilon over 3 times b minus a times b minus a, which is epsilon over 3. So both lower and upper sums differs at most epsilon over 3 units. All right. Well, I have also the following. Then, if I combine all this using triangle inequality, then we have what? Then we get, let me write down, the upper sum for f minus the lower sum for f in absolute value is less than the upper sum for f minus the upper sum for f and 0 plus the upper sum for fn 0 minus the lower sum for fn 0 plus the lower sum for fn 0 minus the lower sum for f. Okay, well, let's see what these things are. Okay, so this thing is less than epsilon over 3. That's the middle term here. It is this one. And okay. Yeah, so where was it? Yeah, both of these are less than epsilon over 3. So these are the first and the last terms of this 3 terms. So all of them are less than epsilon over 3. Epsilon over 3 plus epsilon over 3 plus epsilon over 3. Okay, so what we have seen is then is the following. Let me now summarize what we have done. Given any epsilon, okay, we found some delta, there is some delta, so that if we have a partition P with norm less than P, then the distance, the difference between lower and upper Riemann sums is less than epsilon. Right? This is just epsilon. So hence f is Riemann integrable. Hence f is Riemann integrable. And we have what? We have also we have also this inequality, upper Riemann sum of Fn and upper Riemann sum of F have a difference at most this much for any n greater than n0. Why is that? Well, you see, yeah, here we have this upper Riemann sum. This is true for n0, but not just n0. This is true for all n greater than n0 because of what? Because, all right, so where was it? Yeah, this distance is less than epsilon over 3b times a for any n greater than n0. I used this for n0, but it holds for all n greater than n0. Therefore, this thing actually holds for all n greater than n0, not just n0, but for all n greater than n0. And this thing. So we have this. This is true for all n greater than n0. And finally, we do the following. Let p go to 0 to get what? Here, you see, this thing is true for all n and partition t with norm less than delta. First, I let norm of p goes to 0. If norm of p goes to 0, this upper sums will go to the integral of f n, and this will go to the integral of f, right? Because they are Riemann integrable. So we get this. The first term here goes to the Riemann integral of Fn, And the second thing goes to Riemann integral of f. And this is less than epsilon over 3 for all n greater than n0. So we have what? uh, we are given some epsilon. I choose some n0, so that n greater than n0 implies that this is less than epsilon over 3. In particular, it is less than epsilon. Hence, limit of this gadgets is equal to this. AB f of x dx is equal to the limit as n goes to infinity AB fn x dx. Okay, and this finishes the proof. Okay. Uh, all right. Now, the final thing I'll talk about is series of functions. Series of functions. Do you have any questions so far? Functions. And in this case, in this part, I'll also talk about so-called Weierstrass M-test, which is used a lot in analysis. What's a series of functions? It's like series of real numbers. You have first sequence, and then you just take partial sums, and the sequence of partial sums forms the series, right? So let Fn be a sequence of functions. Let's say Fn. Each of them is defined on some metric space, but I take values in R. Actually, you may also take values in complex number. For example, in complex calculus, you consider functions with values in C. Okay. Define Sn as the nth partial sum. Uh, defined this way. Snx is just f1x, fnx. Okay. If the sequence Snx converges in the submetric, of course, in the supremum metric. So fi's should be bounded functions, of course, in the supremum metric. In, let's say, bx, then we say that the series, which series? Fix, I from 1 to infinity, is convergent, and this summation equals what? Limit of Sn's, whatever that thing is. Okay, as n goes to infinity. So, as in the case of numbers, the sequence, the series of functions defined similarly. Whenever you are given a series, you just look at partial sums. So series means actually a sequence, right? F0, F2, F3, and so on. You look at the partial sums, and if these partial sums converge, then we say that the sum of all fi's is convergent, and the value of this summation is just the limit of the partial sums. Okay, all right. We usually say that the series converges uniformly. we, uh, we usually say that, say in this case, that the series, which series, Fix converges uniformly. Okay. Remember, for a series of real numbers, we have many tests to check convergence, right? P-test, n-term test, ratio test, comparison test, limit comparison test, and so on, many tests. Uh, they have some, of course, here, uh, you know, analogs. And the one which we use a lot is something like comparison test, and that's called Weierstrass M test. Let me now tell you what that is in the remaining time. Weierstrass M test. Okay, so given a series of functions, let's say f and x, and from 1 to infinity or 0 to infinity, where here each fn is a function defined on some metric space with real values, or, as I said, complex, okay, where each fn, of course, is a bounded function, real or complex valued bounded function. Okay, assume that there is a sequence of positive real numbers mn. Okay, so each of them is a positive real number with the following: supremum of fn is less than this number. So this supremum, actually supremum of the absolute values, sorry. Okay, I take the absolute values. Of course, these are all non-negative, therefore this supremum is never negative, but I assume that it is less than mn for all n, and assume that, so the test is the following: if uh, if the series, this series, and from 1 to infinity is convergent, so this is a series of real numbers. If this is convergent, then the series of functions converges uniformly. Okay. Well, how can we prove this? How something is convergent? Well, either you have to have the limit value candidate, and then you compare the limit with the terms of the series, or you can show that this is a Cauchy sequence, right? We know that the metric space of bounded functions is complete. Therefore, whenever you have a Cauchy sequence, you know that it is convergent. So that's what we will do. We don't have a candidate for the limit at this point. We don't have a natural candidate. So we just take the other approach that, bounded functions form a complete metric space. Therefore, any Cauchy sequence is convergent. Okay. All right. So it is enough to show that. Okay. We must show that the series, the sequence, I am sorry, sequence, which sequence? Sn, that partial sums is convergent. Since Bx is complete, it is enough to show that okay, Sn is Cauchy, is a Cauchy sequence. All right, let's see why this is Cauchy. Okay, let epsilon be given. I know that uh, uh, since, let's say, Tn, okay, since this series is convergent, is convergent, the sequence Tn of partial sums of is Cauchy, is convergent, sorry, right? This series is convergent means the partial sums of this is convergent. So T1 is just M1, T2 is just M1 plus M2, and so on, right? Tn is the sum of the first n terms, and this is convergent. And since this is convergent, this is Cauchy. In particular, Tn is Cauchy. Well, since this is Cauchy, I know that epsilon is positive, so there is some n0 so that m and n larger than n0 implies Tn and Tm is less than epsilon. Well, what is Tn and Tm? Tn is the sum of the first n terms. Tm is the sum of the first m terms. So the difference is the sum of the terms between the nth and mth term. So I can just write it this way: Tn plus Tn minus 1 up to Tm plus 2 plus Tm plus 1. The Tm term is gone. So this is less than epsilon. All right. But what is this? Tn was not T. These are M, right? Tn is this thing, so the difference between the nth and mth term is this much. But what is this? Uh, note that uh, fn x is less than mn, right? For all x in x and n. So this implies uh, this thing is less than, right? Each term here in absolute value is less than this. These are all positive numbers and their sum is less than epsilon. So this is less than mn plus m plus 1 and that is less than epsilon. But what is this? This is just snx minus smx. So this is less than epsilon. Right? Sn was the sum of the first n functions. This was the sum of the first m functions. So I have this, and this is true for all m and n larger than n0, right? Hence, Snx converges, is convergent. I mean, converges in the in the metric space, in the supremum metric. Okay, and we are done. Why is that? So, okay, we started with epsilon. There is, I found some n0 such that if m and n are larger than n0, then this distance is less than epsilon. So this finishes the proof. This finishes the proof. So this is a nice way of checking then convergence of series of functions. One example is this. Okay, example is this. Okay. Consider a power series. A power series. an x minus x0 to the power n, and from 0 to infinity. Okay. Let okay r be the radius of convergence. Radius of convergence of the series. Okay. All right. What was the radius of convergence? Radius of convergence is this. This is just lim sub of an plus 1 over an, I guess. Let me just check. If it is, let's say, 1 over n factorial xn, then this should be infinite, is it? So 1 over n plus 1 factorial divided by 1 over n factorial. This is 1 over n plus 1. No, that's not true. So I should have this. Okay. Yes. All right. Well, if this is the case, then you know, on an interval, if this is the case, then if mn is the you know okay, yeah, all right, so here is x0 and I have the radius of convergence r. If you pick any x here, then x minus x0 is less than r. Therefore, x minus x0 to the power n is less than r to the power r. And if you multiply this by an, okay, let me write this way. An times r to the power n. It is less than this. And this condition implies the following. So if you let this to be mn, if you define it this way, by the choice of this, we see that this thing is convergent. So let me leave this as an exercise that this mn, these are all positive numbers, and this is convergent. Is convergent. Well, if this is convergent, then of course by the Weierstrass M test, right? So each term of this series, right? This is my Fn. This is my Fn, let's say Fnx, and its supremum is less than this, right? So this is true for all x. Not this one. This is true for all x. Okay. Yes. This is convergent. It follows from the definition of R, basically. This implies what? So, by the Weierstrass M test, the power series converges uniformly on any interval AB contained in this interval. Okay, you have to take a closed interval like this because you know you don't know what happens at the end points. Radius of convergence means that if you pick a point here, then it is convergent absolutely, but you don't know what happens at the end points. So you have to be careful over there. But this is what we obtain. And if you combine this with the Riemann integrability, we see what? So remark, clearly each fn x, which is an times x minus x0 to the power n, is Riemann integrable. Riemann integrable on any AB contained in this interval. Thus uh, the sum I mean, because they converge uniformly, this is Riemann integrable. So this is Riemann integrable. Integrable. And moreover, uh, the integral of the sum, and if f of x, let's say, denotes this summation, the sum function, then the integral of f over this well, will be just the integral of each term, right? And then you will add it up. So it is just the integral. So this is the limit as n goes to infinity, integral of 0 to n, let's say n a to b. But you see, uh, integral of this is just sum of integrals of this. And what is this? A to B. I'm sorry. Okay, so let me choose here at this point A. This is true for all A, B, but let me choose A to be x0 and B to be any x. Okay, so we get what? We get okay. All right, so So we get the following. Here I have a n and then x minus x0 to the power n plus 1 divided by n plus 1, and this is from x0 to x. So we get okay. So we get what? We get summation from 0 to infinity an, and then I have okay. When you plug x0, you get just 0. So this is just x minus x0 to the power n plus 1 over n plus 1. So what we see is this then the integral of this gadget can be computed as usual. You just take okay. Sanırım internet koptu değil mi? Demin. Şimdi beni evet tamam. So what we have done is this. The integral of a series can be just computed as if it is a polynomial. Okay. You just take the integral of each term separately, and this is what you get. Right. So integral of so conclusion is this. So integral of a series like this. Okay. So x0 to, let's say, x a, and maybe I should write it this way. X minus x0 here. Maybe I should use a dummy variable, right? T, let's say dt. This is just and from 0 to infinity an over n plus 1, and then x minus x0 to the power n plus 1. Okay. All right. Let me just stop at this point.